Welcome to this demonstration of radioactive decay of radon gas. The demonstration is carried out in the framework of the EU RadoNorm project that aims at better understanding and quantifying the health risks associated with radon and norm exposure, as well as finding strategies to optimize protection. At the Stockholm University, we are focusing on analyzing how radon interacts with cigarette smoke in inducing cell damage and consequently cancer. To this end, we have constructed a special cell exposure facility, and we will use this facility for the demonstration. However, the focus of the demonstration is not on the interaction of radon with cigarette smoke. Rather, we want to visualize how radon decays into its daughter products. Now, within the RadoNorm course, within the RadoNorm project, we also organize a course about the biological effects of radiation. This course is organized annually. It is called CELET, and the demonstration is carried out in the course as an exercise. So you will also see some results that were generated during several courses. But before we run the demonstration, let us briefly look at what is radon and what health consequences it causes. Radon is a noble gas that arises in the Earth's crust from disintegration products of the naturally occurring uranium. Now, being a gas, radon leaves the ground and can be captured in a house, as you can see here on the image. And if the house has poor ventilation, then it will not leave the house, but it will stay inside, and the inhabitants will breathe it in. Now, what is the consequence of breathing radon? Numerous studies, like the one shown here, carried out in China, have demonstrated that if you live in a house with a high radon concentration, you run the risk of lung cancer. What is high concentration of radon? That's difficult to say, but you can see in this graph that it went up to 500 becquerels per cubic meter. And you see, if you look closely at the dose response for lung cancer risk, you will see that it starts to be significantly elevated. And we can see this because the 95% confidence intervals, the lower confidence interval, departs from the baseline. The increase starts to be significant at radon concentrations of around 200-300 becquerels per cubic meter. Now, there are houses in various countries where the radon concentration can go up to several thousand becquerels. And if you have ever visited a radon spa, like in Bad Gastein, there the radon concentration is 50-60,000 becquerels per cubic meter. Okay, what is important to remember is that it is not the radon itself that causes lung cancer. Radon is a noble gas, so you breathe it in, you breathe it out. It will not stay in your body. However, radon decays into the metals polonium, lead, and bismuth. And while it decays, it emits alpha particles, and the decay products also emit alpha particles. And the decay products, being metals, will be deposited in the lung tissue, in the bronchi, and they will stay there and cause DNA damage as they emit alpha particles. Now, let us look more closely at how radon arises and disintegrates. So we can draw a matrix for the decay chain of radium-226. Why radium-226? Because this is where radon originates from. Now we have this matrix where on the x-axis we have the atomic number, and on the y-axis we have the mass number of the elements that we will look at in this demonstration. So we start with radium-226 that decays, that has a half-life of 1,630 years. It decays by emitting alpha and gamma radiation into radon-222. And this is what we are interested in. Now radon-222 has a half-life of 3.82 days, and it decays by emitting alpha radiation into polonium-218, as we have already seen. Now, polonium-218 decays again by emitting alpha radiation to lead-214. That in turn emits beta and gamma radiation and is transformed into bismuth-214. That again emits beta and gamma radiation and is transformed into polonium-214. Now, following an alpha particle emission, lead-210 is created that emits beta radiation, is transformed into bismuth-210, and then further on to polonium-210 that finally ends up with or in lead-206. We are interested in radon. So we have constructed at the Stockholm University, or we have acquired a source of radium that emits radon. The source, you can see the source here. This is the source inside the container, but if you open the container, you will see a little flask the size of a match. And this flask is airtight, but it contains radium. It also has two tubes, so it's not really airtight. It contains two tubes that reach outside of the lead containment. Why do we have the tubes? Through these tubes, radon can be extracted. And to this end, we can use a vacuum box like you see here. Now, if we create a vacuum in this box and connect the box via a tube to one of those tubes, then radon will be sucked out of the flask and caught in this box. Now, once we have caught radon in the box, we can place a gamma radiation dosimeter on top of the box and start to measure gamma radiation. Why gamma radiation? Well, this is the radiation that is emitted by these disintegration products. And if we are lucky and catch enough radon, then we should be able to plot the results on a graph where we have the dose rate in microsieverts per hour on the y-axis and the time in minutes on the x-axis. And we hope that we have a dose response. So let's run the experiment and see if we really get such a result.
So now it is time for the real experiment. What we will do here is we will use our radium and radon source to extract radon, catch it in a box, and then we will measure the gamma decay. First, let me demonstrate, and I have here a gamma meter, a dose meter. I will demonstrate to you that there really is gamma radiation emitted by the radon source. Of course, it's not the radon that is emitting gamma radiation, but the disintegration product. Alright, I will turn it off, and I also want to introduce to you the whole facility. Because what is this facility? We are using the facility for the RadoNorm project to study the impact of radon in connection with cigarette smoke on cancer-related changes in lung epithelial cells. So we have the radon source, we have our alpha guard, the dosimeter to measure radon activity, and we have a cigarette smoking machine. So when we run experiments, we suck radon out from the source, it goes to the alpha guard, and the activity is measured. At the same time, we let the machine smoke cigarettes, and the radon and cigarette smoke are mixed in this mixing chamber, and then the gas then is flowing into this cell exposure chamber. Now, cells are cultured in these inserts. The inserts are placed inside the holes. The cover is being put on top so that the cells receive, via these tubes, the cells receive the mixture of radon and cigarette smoke. And then we analyze endpoints that are related to cancer, like DNA damage and things like this. Alright, let's now take some radon out from the radon source in the box. Now the box is a vacuum box, And here I have a pump that I can attach to the box, and I will create an under pressure in the box, and you will be able to see that there is under pressure because we have a manometer here. We have now clamped the tubes that go into the source, so we will have an under pressure here, and once we have built up enough under pressure, we open the clamps and radon will flow into the box. Okay, I will stand now here and I will start pumping. I hope you can see that the vacuum is being built up. You can see the manometer, so it is showing an under pressure. We can go up to, let's say, 330. Okay, we will reach 30. I will stop pumping. Right. Okay, so we have under pressure in the box. What I will do now is I will release the clamps. I am still holding the tube with my fingers. And now I will slowly release the tube. And you will see that the pressure is declining, which means radon is flowing in the box. Okay, so we have now got radon in the box. I will now close this tube, and we can take the box to the lab and start measuring the gamma radiation buildup. Okay, we are now back in the lab with the box full of radon, and the gamma dosimetry has started. We are now counting time 000, and the dose rate is 0.17 microsieverts per hour. We set the clock to 15 minutes, and the next reading will be after 15 minutes. We have now measured gamma radiation buildup for 15 minutes, and the dose rate is 0.83 microsieverts per hour. We will continue the measurement for another 15 minutes. We are now 30 minutes into the measurements, and the gamma dose rate is now 1.25 microsieverts per hour. We have now been measuring for 60 minutes, and the gamma dose rate is 1.83 microsieverts per hour, and we will continue measuring, and the next measurement will be after 30 minutes. We have been now measuring for 90 minutes, and the gamma dose rate is 2.51 microsieverts per hour, and we will now continue measuring for another half an hour. We have now been measuring 2 hours, and the dose rate is 2.64 microsieverts per hour, and this is the last measurement. It's enough to demonstrate the buildup of gamma radiation from radon disintegration. So we have been measuring the buildup of gamma radiation in the outside of the box, because radon has been disintegrating, but there is still radon inside the box. And now we want to measure how much radon there is. What is the activity of the radon? And in order to measure this, we have here an AlphaGuard radon meter, and right now it shows us the background, and you see the background is 375 becquerels per cubic meter. So what we do now is I will attach the AlphaGuard to the tube from the radon box, and I will lift here I will open the lid a little bit so that air can flow in, and we will watch now how much what activity of radon AlphaGuard will measure. AlphaGuard measures in 1 minute cycles, and you can already see that we have exceeded the measurement or the scale of AlphaGuard, because it measures up to 2 megabecquerel, and we have reached 2 megabecquerel. So we have in the box an activity of 2 million becquerels or more, 2 million becquerels of radon.
Now that we run the experiment, let us go through what we have done and what we have achieved. We have extracted radon gas from the radium source, got it in a box. We used an AlphaGuard alpha dosimeter to measure what activity of radon we have caught in the box, and we found that it was more than 2 megabecquerel per cubic meter. 2 megabecquerel corresponds to 2 million becquerels. The activity is probably higher than 2 million becquerels, but we cannot measure it because 2 million becquerels or 2 megabecquerels is the measurement limit of the AlphaGuard. Still, 2 megabecquerels or higher is really quite a lot. Think that inside a house, the most common radon concentrations are in the range of a few hundred becquerels, and here we have 2 million becquerels, so that's not bad. We then used a personal dosimeter to measure the gamma dose rate in microsieverts per hour. Why in microsieverts per hour? Because this is a personal dosimeter, a very sensitive one, and it measures the personal dose equivalent in microsieverts per hour, not in microgray per hour. We then achieved the results, and we can plot them now on a graph. The first where we have a time on the y-axis, on the x-axis, and we have the activity or the dose rate on the y-axis. Now the first result was 0.14 microsieverts per hour. This corresponds to the natural background gamma radiation of approximately 1.2 millisieverts per year. Now the next measurement, 15 minutes later, was 0.8 microsieverts per hour. 15 minutes later, it was 1.27. After 1 hour, we measured 1.83. After 1.5 hours, 2.49. And after 2 hours, 2.65. When we combine the data points, we see that the curve saturates. There is an increase, as we have expected, an increase of gamma radiation with time, but the curve saturates. Now, why does it saturate? Is it because it is so? Or is it because maybe our measurement was not very good? Remember, as I said before, we ran the exercise in the RadoNorm course, Select. In this exercise, we usually have 4 groups of students, and each group runs this exercise. So we have done this in the last course held last year, 2023. And here you can see the results for each group. And here again, we have the dose rate in microsieverts per hour as a function of time. You see that there are quite big differences between the measurements between the groups, and the differences are the outcome of the fact that different groups have managed to extract different activities of radon from the source. Nevertheless, you can see that the curves usually saturate. So this is the way how the curve looks like. There is an increase in gamma radiation, but it's not linear. It starts to decay. Now, how does it look like if we would continue beyond 120 minutes? In an earlier Select course in 2022, we ran such a measurement. We were measuring the gamma radiation over a period of nearly 1 week. And you can see that here you have the initial increase, and you see that it's not linear, it decays a little bit or declines as well, it saturates slightly. And Then somewhere during the night, where we have not done any measurements, there must have been a peak, and the activity or the dose rate started to decline. In the morning of the next day, we were measuring again, and then on day 2, day 3, day 4, day 5, day 6, and the last measurement was carried out during day 7, and you see that the activity or the activity of the gamma activity or the gamma dose rate comes very close to the initial level. Now, this doesn't mean that there is no more decay of radon. Radon has a half-life of 3.82 days, so it will continue decaying over a period of about a month. It's just that our dosimeter is not sensitive enough to pick up gamma radiation when the radon concentration drops below a certain value. Okay, this was the last slide. We hope that you enjoyed watching the presentation, and thank you very much.